A single speck of light could hold the secret to the universe's first fire. From faint glimmers to distant galaxies, each dot hints at the dawn of starlight, and the very first item on our list is a mysterious dot that even seasoned astronomers rarely spot. Stay tuned until number 1. CR7 bursts onto the scene as a massive, luminous galaxy whose bright clumps look like scattered fireflies against the night sky. Discovered in 2015, this distant system glows with an intensity that suggests a swarm of massive, metal-poor stars, potential population 3 candidates. Its unusual spectrum shows strong helium-2 emission, a hallmark of hot, early-generation stars that have yet to enrich their surroundings with heavier elements. Though some researchers argue that the light could also arise from black hole accretion, the prevailing view holds that CR7 offers a rare window into star formation just a few 100 million years after the Big Bang. As we move closer to the next entry, we'll examine a single star whose light was magnified by a cosmic lens, allowing us to see it across billions of light years.
Imagine witnessing a single star from the early universe magnified enough to be seen with Earth's telescopes. That's precisely what happened with Icarus, the most distant star ever observed when it was discovered in 2018. Gravitational lensing by the massive galaxy cluster MAX J1149 amplified its light by more than 1,000 times, turning a faint speck into a detectable point. Icarus is estimated to have existed when the universe was less than 1 billion years old, and its blue-white hue hints at a massive, short-lived star, possibly among the first generations. While its exact metallicity remains uncertain, the fact that it survived the lensing event suggests it was extraordinarily bright, a quality associated with early, massive stars. Coming up next, we'll explore Earendel, another record-setting star that pushes the boundaries of how far we can see.
Earendel, whose name means morning star in Tolkien's Elvish, stole headlines in 2022 as the most distant individual star ever detected, shining from a time when the universe was only about 900 million years old. Like Icarus, its light was magnified by a foreground galaxy cluster, WHL 013708, acting as a natural telescope. The star's luminosity rivals that of 100 million suns, implying it belongs to a massive, possibly metal-poor class, traits expected of the first stellar generations. Spectroscopic analysis hints at a surface temperature hotter than the Sun, and while its exact composition is still debated, Earendel stands as a beacon from the era when the first stars began reionizing the cosmos. Next, we'll travel back a few more 100 million years to meet a star that has earned the nickname Methuselah for its extraordinary age.
Surprisingly, one of the oldest known stars resides in our own galactic halo, catalogued as HD 140283, and affectionately dubbed the Methuselah Star. Its age, estimated at around 14.5 billion years, pushes the limits of cosmic chronology, suggesting it formed shortly after the Big Bang. Spectra reveal an extremely low metallicity, meaning it contains only trace amounts of elements heavier than helium, a signature of early-generation stars that have not been enriched by successive supernovae. While some uncertainty remains about precise age calculations, the consensus places HD 140283 among the earliest survivors, a living fossil from the universe's youth. Up next, we'll examine SMSS J031300.366708393.3, an ultrametal-poor star that may have been forged from the remnants of the very first supernovae.
Found in the southern sky by the Sky Mapper survey, SMSS J031300.366708393.3 is an ultrametal-poor star whose chemical fingerprint suggests it was born from gas enriched by a single, massive population 3 supernova. Its iron content is less than 1/10,000,000th that of the Sun, making it one of the most pristine stellar fossils known. The star's abundance pattern, high carbon and magnesium but almost no iron, matches theoretical predictions for second-generation stars formed from the ashes of the very first explosions. Researchers estimate its age at roughly 13.6 billion years, placing it deep within the epoch when the first stars lit up the cosmos. In the next slot, we'll look at He13272326, another ancient star that challenges our understanding of early chemical enrichment.
Few people know that He13272326, discovered in 2005, holds the record for the lowest iron abundance ever measured in a star, with an iron-to-hydrogen ratio about 100 millionth that of the Sun. Such a scarcity indicates formation from gas polluted by the very first generation of massive stars, before the universe became enriched with heavier elements. Its surface also shows unusually high carbon and nitrogen, a pattern that aligns with theoretical yields of early supernovae. Age estimates place He13272326 at roughly 13 billion years old, making it a prime candidate for a second-generation star that directly inherited the chemical legacy of the first stellar explosions. Coming up, we'll travel to J03136708, a star that may be even older and even more pristine.
Hidden among the Milky Way's halo, J03136708 has captured attention as possibly the oldest known star, with an estimated age of around 13.9 billion years. Its spectrum reveals an exceptionally low iron content, less than 1/10,000,000th of the Sun's, yet it possesses a surprising amount of carbon and magnesium. These signatures imply formation from material enriched by the very first supernovae, making J03136708 a direct link to the universe's first luminous objects. While precise dating remains challenging, its chemical fingerprint is among the most extreme ever observed, reinforcing the notion that pockets of pristine gas survived long enough to birth low-mass stars we can still observe today. Next, we'll examine SDSS J102915+172927, a star that pushes the limits of what we consider possible for early low-mass star formation.
Remarkably, SDSS J102915+172927 challenges the long-standing belief that the first low-mass stars could not form without sufficient metal cooling. Discovered in 2012, this star exhibits an iron abundance roughly 1/200,000th that of the Sun, and an overall metallicity below the critical threshold thought necessary for fragmentation of primordial gas clouds. Yet it exists as a low-mass, long-lived star, suggesting alternative cooling pathways, perhaps via molecular hydrogen or dust, allowed its birth. Its age, estimated at about 13 billion years, places it firmly in the early universe, making it a key piece of the puzzle regarding how the first stellar populations transitioned from massive, short-lived giants to the smaller stars that survive today. Up next, we'll turn our gaze to a distant galaxy, GNZ11, which may harbor the very first star clusters.
Astronomers have long chased the earliest galaxies, and GNZ11 stands out as one of the most distant known, observed when the universe was a mere 400 million years old. Its extreme ultraviolet brightness hints at a burst of massive, metal-poor stars, potential population 3 candidates, lighting up the cosmic darkness. Spectroscopic measurements reveal a surprisingly low metallicity and a high ionization parameter, both consistent with a youthful, star-forming environment. While the galaxy's exact stellar makeup remains under study, its properties suggest it could host clusters of the first stars, making it a valuable laboratory for early universe physics. Finally, we'll conclude with the faint ripples in the cosmic microwave background, the ultimate dots that may have seeded the first stars themselves. We've traveled from the bright blaze of CR7 to the subtle ripples in the cosmic microwave background, each dot offering a glimpse into the universe's earliest moments and reminding us how much wonder still lies hidden among the stars. If you enjoyed this journey into the unknown, hit the like button and subscribe so you don't miss the next mind-blowing list we drop each week. Which dot sparked your curiosity the most? Share your thoughts below, and let's keep the conversation going.